The calculations for a hypothesis test for one population mean. The first step in the calculation for a test for one mean is to take a sample from the population and compute the sample mean. If the population standard deviation is known or assumed, we use the normal distribution to determine if x bar is too far away from the hypothesized value of mu using the test statistic z, which is the z-score of x bar, computed by taking x bar minus the hypothesized population mean mu divided by the standard error of x bar, that is, sigma over the square root of n. For example, if x bar is 46 and the hypothesized mean is 50, the numerator is 46 minus 50, or negative 4. If the population standard deviation is assumed to be 14 and the sample size is 100, the denominator is 14 over the square root of 100, or 1.4. So z is negative 4 divided by 1.4, which is negative 2.86. On the other hand, if the population standard deviation sigma is not known or assumed, we use the sample standard deviation s to estimate sigma. The test statistic t is the estimated number of standard deviations that x bar is from the claimed value of mu, and is calculated by taking x bar minus the hypothesized population mean mu divided by s over the square root of n. For example, if x bar is 32 and the hypothesized mean is 30, the numerator is 32 minus 30, or 2. If the sample standard deviation is calculated to be 4 and the sample size is 25, the denominator is 4 over the square root of 25, or 0.8. So t is 2 divided by 0.8, which is 2.5. To determine if an observed x bar is too far from or fairly close to mu, statistically speaking, we can use either a critical value or a p-value approach to determine whether or not there is evidence to reject the null. These calculations depend on the assumed level of significance, called alpha, and also whether we are doing a two-tailed test, where the null is that the population mean equals some hypothesized value and the alternative is that it is not equal, or a one-tailed right-tailed test, meaning that the alternative hypothesis, what we suspect or are trying to prove, is that the population mean is greater than the claimed value, or a one-tailed left-tailed test, where the alternative is that the population mean is less than a claimed value. First, suppose we are using a critical value approach. For a two-tailed test, we identify critical values on a standard normal or t-distribution with n-1 degrees of freedom that cut off alpha percent of the probability to the outside of those critical values. For example, for a normal distribution, for a 5% level of significance, the critical values would be positive 1.96 and negative 1.96. If we had a t with, say, 19 degrees of freedom, we find critical values of 2.093 and negative 2.093 give 5% of the probability outside them, and we reject the null if the test statistic is outside these values. For a one-tailed right-tailed test, we find the critical value that cuts off alpha percent of the probability to the right. For example, for a normal distribution and a 5% level of significance, the critical value would be positive 1.645. If we have a t-distribution with 15 degrees of freedom, 5% is the probability to the right of 1.753, the critical value. We reject if the test statistic is greater than the critical value. For a one-tailed left-tailed test, we use the critical value that cuts off alpha percent of the probability to the left. For example, using a normal and a 10% level of significance, the critical value would be negative 1.282. If we had a t-distribution with 24 degrees of freedom, 10% of the probability is to the left of minus 1.318. For this left-tailed test, we reject if the test statistic is less than these critical values. This process can be generalized to any level of significance, and for a t-distribution, any degrees of freedom. Next, to explain the p-value approach. For a two-tailed test, the p-value is the probability that the distribution is outside the test statistic, z or t, and it's negative. For example, if the test statistic was z equals 2.1, we would find the probability that a standard normal is outside 2.1 and negative 2.1, which is 0.0357. On the other hand, if the test statistic was t equals 1.88 and the sample size was 21, we would find the probability that a t with n-1 or 20 degrees of freedom is outside 1.88 and minus 1.88, which is 0.0748. We always reject if the p-value is less than alpha. In this case, if alpha was, say, 0.01, we wouldn't reject either of these hypotheses because both p-values are greater than alpha. For a one-tailed right-tailed test, we calculate the probability that the appropriate distribution is greater than the test statistic. For example, if we had a z-statistic equal to 2.1, the probability that a normal is greater than 2.1, that is, the p-value, is 0.0179. For a t-statistic, say t equals 1.4 with a sample size of 26, we find the probability that a t with n minus 1 equals 25 degrees of freedom is greater than 1.4, which is 0.0869. Again, we reject the null if the p-value is less than alpha. For example, if alpha were equal to 10%, we would reject in both of these cases because both p-values are less than 0.10. For a one-tailed left-tailed test, the p-value is the probability that the distribution is less than the test statistic. For example, if the z-statistic was negative 1.7, the p-value, that is the probability that a normal is less than negative 1.7, is 0.0446. If we had a t-statistic, for example, negative 1.99 and a sample size of 12, the p-value is the probability that a t with n minus 1 or 11 degrees of freedom is less than negative 1.99, which is 0.036. As always, we reject if p is less than alpha. For example, if alpha were 0.05, we would reject in both these cases because both p-values are smaller than 0.05.